Okay, guys, today we're going to learn a new skill in this chapter. So before we start, hopefully you have your Chapter 5 guided notes out, and you will need a calculator today. You will need one, so make sure you have a calculator. So let's talk about this. It says using a graph to determine the rate law. So the rate law, which we've been studying a lot in the past couple of lessons, must be determined experimentally. So we just got done doing a lab where we determined the rate law experimentally. You actually did the reactions, timed them, and figured out the rate law. Well, a chemist can graph the concentration of reactants versus time to determine the effect of concentration on the rate of a reaction. But this involves using calculus to determine the area under the curve, which is beyond the scope of this course. We're not going to do calculus. So we're going to simplify this process by using equations that have already been derived to determine the rate law. By using graphs to find the rate law, you can determine the concentration of a reactant at a specific time, which is incredibly useful for chemists. Let me say that again. By using graphs to find the rate law, you can determine the concentration of a reactant at specific times. The integrated rate law, this is what this lesson is about. The integrated rate law expresses how the concentrations of reactants depends on time. The integrated rate law expresses how the concentrations of reactants depend on time. Using the integrated rate law equations allows us to find the concentration of a reactant at a certain time after the reaction has started. So we might pick a time like 10 seconds after the reaction starts. And by using these integrated rate law equations, we can calculate what the concentration will be after that 10-second time period. Or maybe we want to know the concentration after a month. We can figure that out using these integrated rate law equations. They're incredibly useful. So here's some graphs I'd like to go over. This one on the left is, you always should look at what the axes are reporting on a graph. This is reporting concentration, and the x-axis is reporting time. And then it tells you what zero order, first order, and second order would look like. How the concentration changes with respect to time. Now let's look at this graph on the right. This one is the rate, so molarity per second, the actual rate of the reaction plotted against its concentration on the x-axis. And you'll notice that the rate is not affected by the concentration in zero-order reactions. In first-order reactions, the rate is proportional to the concentration of the reactant. And in second-order, you see this curved line, and that's because the rate is going to be quadrupled when you double the concentration of A, and so you see this curved line here. So we're going to use these today. Another thing that we're going to learn today is half-life. Half-life is abbreviated by chemists by T to the 1/2. So when you see this T to the 1/2, that means half-life. So half-life of a reaction is the length of time it takes for the concentration of the reactant to fall to half of its initial value. So I've got a graph of this over here. Time is on the x-axis, and concentration is on the y-axis. So take a look at that for a second, and I'm going to ask you, what is the half-life of this reaction here? What is the half-life of that? Yeah, so if we're at time 0, we're at what concentration? 1 molar. So we want to know the time that it takes to get this concentration to fall to half of its value. Half of its value would be 0.5. How much time did that take? 100 seconds. So in another 100 seconds, so when we get to 200 seconds, we're not going to be at 0.5, but we're going to be at what? 0.25. And in another 100 seconds, we're half of 0.25, which is 0.125. The half-life of a reaction depends on the order of the reaction. So this amount, this time, this half-life, depends on the order of the reaction. Okay, now let's get into what we're really going to learn about today. And these are the integrated rate law equations. We're going to go over those equations for zero order, for first order, and for second order reactions. So let's start with zero order reactions. We've already learned the rate law for a zero order reactions. The rate is equal to the rate constant times the concentration of the reactant raised to the zero power. But would chemists write this? And the answer is no, because anything raised to the zero power is 1. And so rate is equal to k. That's the rate law. Rate is equal to k. Now, what we can do is use calculus to take this rate law, and they use calculus, and what they do is they integrate it or use an integral of this reaction. And when you do that, you come out with an integrated rate law equation, which is right here. Okay? This is the integrated rate law equation for a zero order reaction. Now, when you integrate the rate law, it puts it into a form that should be fairly familiar to us. When you integrate this, it puts it into this form. So y, so the concentration of A would be our y, is equal to a minus mx plus b. Have you guys seen this equation before? That's the line slope equation, isn't it? When you're graphing in your math class, you've probably gone over this. But this is the y value is equal to minus m. What is m, guys? Slope. And what is b? That's your y-intercept. So when we have this integrated rate law, this is going to be the y value on the graph is equal to the minus k. The minus k is our slope. On our x-axis, we're not calling it x, we're going to call it time. So it's got t right there. Plus, the initial concentration of A is going to be our y-intercept, or where it crosses the y-axis. So like it says here, a graph of the concentration of A versus time is a straight line, with the slope being minus k and the y-intercept being the concentration of A initially. The half-life of a zero order reaction is given by this equation. So the half-life would be the concentration of A initially divided by 2 times the rate constant. Okay, now let's look at this graph down here. Our y value is the concentration of A at some time. That's going to be our y value. Minus k is our slope. So the slope is negative on zero order reactions. And our y-intercept is the concentration of A initially. So wherever your initial concentration of A is, that's where it crosses this y-axis. That's your y-intercept. Okay, now let's look at the same thing, but for a first order reaction. So we know the rate law of a first order reaction. Rate is equal to k times the concentration of A raised to the first power. Now chemists don't write the 1 here. So your rate is equal to k times the concentration of A. That's your rate law. Now if you use calculus and take the integral of this equation, what you get is the integrated rate law. That's the most important thing on this slide. The integrated rate law for a first order reaction is the natural log of the concentration of A at some time is equal to the minus k times t plus the natural log of the concentration of A initially. again, this follows the line slope equation. This would be our y value. It's equal to a minus mx would be this value here, plus b. Our y-intercept is going to be, this time, the natural log of a initially. The half-life of a first-order reaction. We're going to use this equation a lot in the coming days. Half-life of a first-order reaction is given by this equation, is equal to 0.693 divided by the rate constant. And the half-life for first-order reactions is constant. Okay, let's look at a first-order graph. So again, this is our integrated rate law. Now let's look at the graph of it. Our y value is going to be the natural log of the concentration of your reactant at some time. It's equal to minus k is going to be your slope. So again, it has a negative slope. And our y-intercept is going to be the concentration of your reactant initially. So what you start at. That's where it crosses your y-axis. Okay, the half-life of first-order reactions is constant. So if it's 100 seconds in the first half-life, the second half-life is going to be also 100 seconds. And so this half-life is constant. Okay, now finally, let's look at second-order reactions. The rate law is equal to K times the concentration of your reactant raised to the second power. So this would be second order with respect to this reactant concentration. Now if you use calculus on this rate law equation and integrate it, take the integral of that equation, you're going to get the integrated rate law for a second order reaction, which would be 1 over the concentration of A at some time is equal to KT, rate constant times time, plus 1 over the concentration of your reactant initially. Again, it's going to follow the equation of a line. Y is equal to a mx plus b. The half-life of a second order reaction is given by this equation here. Half-life is 1 over the rate constant times the initial concentration of your reactant. If we look at the graph for a second order reaction, this is the integrated rate law. This is our y value is equal to mx plus b. So our y value here is 1 over the concentration of your reactant. The slope now is positive for second order reactions. Slope is equal to k. We're not calling it the x-axis. Time is represented on our x-axis, so it's t. Plus 1 over the initial concentration of your reactant is your y-intercept. So that's where it crosses the y-axis right down here. Okay, here's a slide that summarizes everything that we just talked about with the integrated rate laws. Okay, for zero order, the integrated rate law equation is right there. For first order, your integrated rate law equation is right here. And for second order, your integrated rate law equation is given here. It also shows you the graphs and also the half-life equations for each one of those. I will give you this information. In fact, the packet, this yellow packet that I passed out before class, has all of that information on it. And you will be able to use this on all of the worksheets, the study guide, and the test. So you will not be expected to memorize this stuff, but you will be expected to know how to use these equations. So I've got some practice problems. There's 4 practice problems that are going to follow. And we're going to use these equations and actually see why a chemist would use them. So let's go to practice problem 13. It says the decomposition of a certain insecticide. Do you guys know what an insecticide is? An insecticide is a chemical spray that they spray, and it kills what? Insects. So the decomposition of this insecticide in water follows first order kinetics. I want you to underline what I'm underlining. Okay, it's a first order reaction with a rate constant of 1.45 per year. So our time value there is years at 12 degrees Celsius. A quantity of this insecticide was washed into the lake on June 1st, leading to a concentration of 5.0 times 10 to the minus 7th grams per centimeter cubed. Assume that the average temperature of the lake is 12 degrees Celsius. Okay? So we've got this pesticide. It follows first order kinetics. It gave us the rate constant. It also told us the concentration there. Now let's answer the question. Part A. What is the concentration of the insecticide on June 1st of the following year? So would this be useful for a chemist to be able to figure out? If you spray this lake with a pesticide, and you know the concentration of the lake right after you sprayed it, would it be useful to know what the concentration of that insecticide will be 1 year later? Sure. Maybe you're doing some study on whether or not you can introduce fish back into the lake, or you know, what the lethal limit of this insecticide's concentration is. Maybe you want to figure out when it's going to become safe to introduce fish back into the lake again. Anyway, there's a lot of real-world applications here and why a chemist would use this. So let's go through how to solve this. First of all, it is first-order kinetics. So let's write the integrated rate law equation down for first-order reaction. Okay, it's on that packet that I gave you. So if you look there, the integrated rate law for a first-order reaction is the natural log of the concentration of the reactant at some time is equal to a minus K, which is your rate constant, times time, plus the natural log of the concentration of your reactant initially. So sometimes you'll see this little zero sign here. This means initial. Please make that note. I call it a not symbol. It means initial. Now we're going to plug into the integrated rate law. We're going to plug all the variables in that we know. Do we know the concentration after that time? Or is that what it's asking us to find? Yeah, that's what it's asking us to find. So we're just going to keep the natural log of A at some time the same. Did it give us the rate constant? Yeah, it told us that the rate constant was 1.45 per year. So notice there's a negative sign here. So minus 1.45. Now we're going to times this by t. T is the time that it's asking for. How much time has elapsed? 1 year. So we're going to put 1, and it's in year, and my rate constant was in years, so that's okay. So we're just going to put 1 right there for the 1 year time period, plus the natural log of the concentration of this initially. Did it give us the initial concentration? It did. So the natural log of 5.0 times 10 to the minus 7. Now we have an equation with one unknown, and that is the concentration of this insecticide at the end of that 1 year time period. So we're going to solve for this right here. So here we go. Here's how I would do it. Okay, let's simplify it as much as we can. We've got the natural log of the concentration of our reactant at some time is equal to a minus 1.45 times 1 is still minus 1.45 plus the natural log of 5.0 times 10 to the minus 7. Now let's grab a calculator and take a minus 1.45 and add the natural log. Do you guys see where the LN button is on our calculators? It's the third one down on this column here, the far left column. So natural log, and it puts parentheses in for you. 5.0 times 10 to the minus 7th. And so I get this. The natural log of A at some time is equal to a minus 15.96. Is that what you guys got? Okay. Now, a bit of a math trick. I don't know if you've learned about logarithms and natural logarithms, but what's the opposite of natural log? E. The inverse of natural log is E. So if we want to get A, the concentration of A at some time by itself, we need to do the opposite of that. Usually we would divide by natural log, but the inverse of natural log is E. So we can get rid of natural log by taking and doing E to that power. So here's what I mean. The concentration of A at some time is going to be equal to E to the minus 15.96. Did you follow what I did right there? So the opposite of natural log is E. And so if we take it and times E by both sides, you're going to have to raise that to that power. So do you see where the E button is, guys? You have to hit the second function on our calculators and type in negative 15.96. And what do you get? Very small number. So let's put that in scientific notation. And so our concentration of this insecticide after 1 year is going to be 1.17 times 10 to the minus 7th. And what were my units? Grams per centimeter cubed. Okay, grams per centimeter cubed. So after 1 year, did the concentration of that insecticide decrease? We were at 5 times 10 to the minus 7th, and after 1 year it's going to decrease to 1 times 10 to the minus 7th. So it did decrease like we would expect. All right, that's part A. Now let's go to part B. And I've got some writing over the top of it, but I think we can still see it. How long will it take for the concentration of the insecticide to drop to 3 times 10 to the minus 7th? So we can use this equation to solve for the concentration at any time value that we put in there. And so here's how we would do that. Okay, I'm going to write small and try to do it over here. So again, we're using this equation, the natural log. What was the final concentration? Yeah, 3. It's this, 3 times 10 to the minus 7th. We're going to set that equal to a minus k. Does the rate constant, is that still the same? Yeah, it's constant. So 1.45, but we've got to remember the negative sign, 1.45. Times, now do we know t? In this case, we don't know what t is. It says how long will it take? So we're going to solve for that. Plus the natural log of A initially. What was the concentration initially? Yeah, it gave it to us in the problem. 5 times 10 to the minus 7. Now we just use a calculator. What I would do is let's subtract the natural log of 5e to the minus 7th from both sides. So let's take the natural log of 3 times 10 to the minus 7th and subtract off the natural log of 5 times 10 to the minus 7th. And so that equals a negative 0.51, and that's equal to a minus 1.45 times t. How do we get t by itself? How do we get this t by itself, guys? Divide by minus 1.45. So let's take that and divide it by a negative 1.45. And what do we get for t? 0.35. 0.35, what are the units for t in this equation? Or in this problem? Yeah, we were measuring, the rate constant was measuring per year. So that's 0.35 years, or just over 1/3 of a year. It will be at that concentration. Okay, there's a lot to it, isn't there? But can you see the value of this for a chemist? I hope so. You can figure out the concentration of this substance at any time period throughout the year with the integrated rate law. All right, so let's see if we did get it right. I'm sorry about writing over the top, but I think we did, right? 1.17 times 10 to the minus 7th and 0.35 years. So we did get it right. Okay, let's go to practice problem 14. It says the decomposition of dimethyl ether at 510 degrees Celsius is first order process with a rate constant of 6.8 times 10 to the minus 4th per second. Okay, this is dimethyl ether. It's decomposing. Looks like it's forming some methane gas, some hydrogen gas, and some carbon monoxide gas. Let's answer this question. If the initial pressure of dimethyl ether is 135 torr, what is the partial pressure after 1,420 seconds? Now this brings up an important point. For gases, we can measure the concentration of the gas in terms of the pressure. And so torr is a unit of pressure, but we can substitute that into the equations just like if it was its concentration in terms of molarity. All right, so what should we underline in this equation? Yeah, first order process. So we're going to use the first order integrated rate law equation again. Let's write that down. Okay? The first order integrated rate law is the natural log of the concentration at some time is equal to a minus kT plus the natural log of your concentration initially. Now let's substitute in our variables and solve what it would like us to solve for. Okay, the natural log of A finally, that's what we don't know. So I'm just going to keep calling it the natural log of A at some time. It's equal to, did it give us the rate constant? It did. But we still have to keep this negative sign in. So remember this negative sign. So minus 6.8 e to the minus 4th. Times time. Now be careful right here. The time that it gave us was 1420. But what units? Seconds. What units were the rate constant in? Seconds. So do they line up? Yeah, they do. And so we don't need to do any conversions here. But if this was, say, I don't know, minutes, and they gave us seconds here, you would have to convert to like units. So just be aware of that. But this one, easy. 1420 we can put in right there because it's seconds. Now, add the natural log of the concentration initially. Did it give us the concentration initially? Yeah, it said the initial pressure was 135 torr. Can we just substitute pressure in if it's a gas? Sure. And so it's the natural log of 135. Perfect. Now we've got a math equation with one unknown. We're going to be solving for this value right here. So what I would do is simplify this. The natural log of a at some time is equal to, let's multiply these two values together, minus 6.8 e to the minus 4th times 1420. Okay, and that's a negative 0.9656. And then let's add the natural log of 135. And so what I get if I do that is that the natural log of a at some time is equal to 3.94. 3.94. Now, what's the opposite of natural log? E. So we can cancel out our natural log on this side if we do that. So we've got a at some time is equal to e to this power, 3.94. So let's do that. And when we do that, the concentration of A at some time is equal to 51.4. Now what are my units going to be? 51.4 what? Torr, yeah, that's, we weren't measuring in terms of molarity. This is 51.4 torr. Okay, so perfect. So after 1,420 seconds, the pressure is going to decrease to 51.4 torr. All right, I've got a couple more practice problems with these, and we did get that one right. So let's go to practice problem 15. Whoops. Okay, and so let's read it. It says the reaction, and they give us this equation here, is first order. I want you to, well actually, how about you guys try this one on your own? Okay, so I'm going to hit pause. I want you guys to try it. See if you can't do this one. If you're watching the video, please hit pause at this point. Try it on your own. And once you have your answer, hit play and see if you got it right. All right, so I went ahead and solved this one. And hopefully you guys, at this point, you have an answer too. But let me just run down the quick version of this problem. It is a first order reaction. So I wrote down the first order integrated rate law equation. Then I simply just used the information and plugged in the values here. And when you solve it correctly, you should get that the concentration after this 865 seconds will be 0.0175 molar. Hopefully you got that answer as well. Okay, let's go to the last practice problem for this lesson. It's practice problem number 16. I would like you guys to try this one on your own as well, but be careful with this one. This one says second order. So you're going to use the second order integrated rate law equation. Please try it on your own. If you're watching the videos, hit pause right now. And once you have your answer, hit play and see if you got it right. Okay, so I went ahead and solved it, guys, and hopefully you can follow what I did here. This is the second order integrated rate law. We plugged in our values. I took this one in my calculator first and subtracted this value. And I got 900. 900 is equal to k times, now 5 times 10 to the second is 500, so I just simply put 500 there. Then to get k by itself, 900 divided by 500, k is equal to 1.8. Now the units here are going to be molarity to the minus 1, seconds to the minus 1, but we did get that one right. And so hopefully you followed me through and can solve for k in that practice problem. Guys, we're done with the lesson. I've got some more practice with these types of problems in the student workbook. There's a worksheet. It's titled Integrated Rate Law Worksheet. So please go there now and let's get that done. Again, it's called Integrated Rate Law Worksheet. and hopefully this video helped you.